Terrestrial radio transmission is governed by immediate physical constraints. Low-frequency ground waves dissipate their energy as heat into the Earth's crust, while high-frequency space waves travel in straight lines, unable to follow the planet's curvature. A signal aimed at the horizon either loses its strength to the ground or shoots directly into the vacuum of space. Sustaining over-the-horizon communication requires the use of skywaves, radio signals that utilize the upper atmosphere as a refractive medium to bend back to the surface. This medium is the ionosphere, a stratified layer of plasma located between 50 and 2,000 kilometers above the Earth. Reliable long-range communication depends on the ability to predict the behavior of an invisible, continuously shifting fluid of charged particles. Refraction occurs because free electrons in a plasma increase an electromagnetic wave speed. When a radio wave enters the ionosphere at an angle, its upper edge encounters these electrons first, accelerating and pivoting downward, forcing the signal into a curve that returns toward Earth. The intensity of this curve is frequency-dependent. Low-frequency waves are easily deflected by low electron densities, while higher frequencies require much denser plasma to achieve the same downward turn. If a signal's frequency is too high for the current density of the layer, the wave will not bend enough to return to the surface. It will simply pass through the plasma and into space. Selecting the correct frequency for an HF circuit involves matching the refractive curve of the wave to the specific distance required to reach a receiving station. The density of the ionospheric plasma is driven by solar radiation, specifically extreme ultraviolet and X-ray emissions. When these high-energy photons strike neutral atoms in the atmosphere, they strip away electrons, creating free ionization. This is balanced by collisional recombination, where free electrons and positive ions collide and regroup into neutral atoms. Different solar wavelengths lose energy at different altitudes, creating distinct density layers, D, E, and F. In the loosely packed F region, plasma persists throughout the night, but in the dense lower D region, rapid atomic collisions cause instant recombination once the sun sets. As the sun sets, the dense D layer rapidly decays, losing its ionization and effectively disappearing completely until dawn. This predictable relationship between radiation and altitude forms the Chapman model, suggesting ionization levels can be calculated purely by the angle of the sun. According to this theory, the ionosphere would behave as a stable, predictable mirror, tied directly to the time of day. Empirical data shows the ionosphere functions as a complex electrodynamic fluid, with its density determined by forces beyond simple solar exposure. Under the Chapman model, maximum plasma density should occur directly over the geographic equator at noon. Instead, data shows that the highest concentrations split and move away from the equator. Measurements from the ISIS-1 satellite reveal a deep trough in electron concentration at the magnetic equator, exactly where solar radiation is most intense. The missing plasma is found in two asymmetrical crests of high density, located roughly 20 to 30 degrees north and south. This is the equatorial fountain. Eastward electric fields interact with the horizontal magnetic field, creating an upward force that lifts plasma away from the equator. Reaching high altitudes, the plasma slides down curved magnetic field lines, pooling into the dense crests observed by satellites. Radio propagation planning must account for this magnetic topology, which physically redistributes the medium away from the solar zenith. The high-latitude ionosphere is subject to even more volatile shifts, driven by the vertical orientation of the Earth's magnetic field at the poles. Measurements of the Alaskan ionosphere show extreme latitudinal gradients, where electron density changes abruptly. Equatorward of the auroral oval, nighttime densities can plummet by an order of magnitude, creating a trough that acts as a physical boundary to signals. High-latitude circuits also face the threat of polar cap absorption, triggered by solar proton events. During solar eruptions, high-energy protons are funneled toward the Earth and guided by magnetic field lines directly into the polar atmosphere. These protons strike the low-altitude D layer, causing a massive, sudden increase in ionization. This turns the layer into an impenetrable absorber that can completely block radio signals for several days. Closing polar radio links requires signals to survive space weather events that are concentrated and guided by the Earth's magnetic geometry. Maintaining reliable circuits through these constant environmental shifts requires more than theoretical modeling. Engineers utilize the Ionosonde, a sweep-frequency radar that fires radio pulses straight up into the atmosphere. By timing the return of these echoes across a range of frequencies, the Ionosonde identifies the exact height and density of each ionospheric layer in real time. This data allows operators to determine the maximum usable frequency, the upper limit a signal reaches before it fails to refract and escapes into space. Physics-based models provide the theoretical foundation, but maintaining a circuit requires the continuous empirical measurement of the local atmosphere. The ionosphere remains a volatile medium that must be actively navigated to enable long-distance communication. Transmission requires a frequency high enough to minimize absorption in the dense D layer, but low enough to ensure the F layer can still pivot the wave back to Earth. This operational window is constantly moving, influenced by diurnal shifts, the equatorial fountains, and auroral disturbances. Operators maintain the link by dynamically adjusting frequency and power to match the shifting currents of the atmosphere. Global high-frequency communication relies on the continuous, real-time synchronization of transmission parameters with the fluctuating properties of the ionospheric plasma.